Okay, so now we'll see how the advanced encryption standard AES works. So AES works based on it's a block cipher, and the block length is 128 bits, and the key length could be either 128 bits, 192, or 256 bits. And like DES, ACE also works based on the rounds, and the number of rounds could vary depending on the key length. So for 128 bit key, the number of rounds is 10. 192 bits is 12 rounds, and 256 bits is 14 rounds. Uh, so each round works identical to the other round, except the last round. So each round consists of the following sub steps. So we call there's a substitution step that's done at the byte level. So then we have two permutation steps. One is a row-wise permutation, and the other is a column-wise kind of mixing of the columns, both done at the word level, and then there is an XOR operation done with the key for a particular round. So we are going to see the details of each of the sub-steps. Um, so the first thing about the input block. As I said, the input is like 128 bits. So the 128 bits are arranged as a 4 by 4 matrix of bytes. So each byte is like 8 bits. So we have 16 cells, and 16 times 8 is 128 bits. So this is how the input bits are arranged. And again, this matrix is filled in a column-wise order. So you have the first byte, 0, byte 0, byte 1, byte 2, byte 3, and then byte 4, byte 5, and so on. And also, we'll use a terminology called word. A word is basically a collection of 4 bytes. So a word is 32 bits. So we'll call each column as a word, because each column comprises of 4 bytes and it's a word. Okay. And so we call this as input block initially, and as we go through each round, we still have a 128-bit block. So we call the block at each round as a state array. So we'll have a state array entering a block, entering a round, and leaving as an output state array. Okay. And we'll work with basically hexadecimal values. So just to know what are how to represent hexadecimal values. 0 to 9 in decimal, or simply represent as 0 to 9 in hexadecimal. But 10 in hexadecimal is A, 11 is B, 12 is C, 13 is D, 14 E, and 15 is F. So I said we use the key length could be either 128 bits or 192 bits or 256 bits. For this discussion, we'll refer to only 128-bit key. So the 128-bit key is basically arranged like the input block array as a 4 by 4 array. If you use a 192-bit key, it's arranged as a 4 by 6 array, so which means there'll be 4 rows and 6 columns. And if it's a 256-bit key, it's arranged as a 4 by 8 array, which means there'll be 4 rows and 8 columns. Okay. So the as I said, we'll just deal with 128-bit keys. The only difference is going to be the number of rounds that AES will run. So with 128-bit key, we'll run 10 rounds. So the way it works is, before we start the first round, we'll XOR the input block. We'll XOR the 128-bit input block with 128-bit key. So because each is the key is like 128 bits, which means it is like 16 bytes, and so that's just 4 word quantity. So we will generate basically 4 the 4 words for each round will be different. So this is like what we call the expanded key. So using that 128-bit key, will expand. It's just 128-bit key is like a 4 word quantity, like each row, each column is a word. we'll expand that 4-word key to basically 44-word key schedule. Okay, so the initial XOR round, the operation or step will take up the first 4 words of the key schedule. Then round 1 will take the next 4 words of the key schedule. Then round 2 will take the next 4 words, and so on. So the round 10 will use the last 4 words of this key schedule. So that's where I show that the 4-word key is being expanded into what we call as a key schedule, and this key schedule for the 128-bit key is going to, or 4-word key, it's going to be 44 words. Now when we do decryption, the decryption in AES is done in a different order compared to DES, where in DES both encryption and decryption are almost the same, only the you go from L0, R0, L1, R1 and so on in encryption, whereas decryption will go from L16, R16, L15, R15 and so on. But for both encryption and decryption in DES, we use the Freestyle network, which is the same. Whereas in AES, the encryption and decryption are kind of done in a different order, even though they are related to each other, as we'll see. So in decryption, we'll use the last 4 words of the key schedule to do the kind of the initial XOR operation with the ciphertext block, and then whatever comes out of it goes to rounds 1, 2, 3 up to 10. So for round 1, we'll use the 36th to 39th word of the key schedule, and so on. And round 2 will use the 32nd to 35th word of the key schedule. And round 10 will basically use the first 4 words of the key schedule. So if it is a 192-bit key, as I say here, we'll have a 4x6 array. So which means if we do the math, and 192 bits will require 12 rounds. So if I ask you to compute the length of the key schedule, so it's a 4x6 array. So it's a 4x6 array for 192-bit key. So basically we'll have 6 words, because each column is a word, and we have 6 columns for the input key. So we have 12 rounds for 192-bit key. So we need 12 times 6, which is 72 words for the 12 rounds. Plus for the initial XOR operation, we need 6 words. So we need a total of 78 words for 192-bit key. Now if it is a 256-bit key, it's going to be a 4x8 array, right? So it's going to be then 8 words per round, and we have a total of 14 rounds, plus so that will be like 8 times 14 plus the initial 8 words for the initial XOR operation. So that's going to be 8 times 14 plus 8, which is 120 words. So this is the length of the key schedule for the 192 bits and 256-bit keys. Okay, so we'll continue. So the encryption decryption in a particular round happens as follows. So this is the encryption round. So as I said initially, we'll have these 4 sub-steps. So in each round, what we'll do is we'll go through the substitute byte step and the shift row step, followed by the mix column step, and then we'll do the XOR operation with the round key. So addition, when I say addition in AES, it typically means XOR operation. And the decryption round proceeds like this. We'll go through first the inverse shift row step, the inverse substitute byte step, then the XOR operation with the round key. So this is the 128-bit key taken from the key schedule. Okay, so when I say round key, that's basically it is coming from the key schedule, and then followed by the inverse mixed column step. So as you can see here, the sequence, the order in which we do go through the sub steps is different for an encryption round and different for a decryption round. Also, there's a small thing that the last round of encryption does not involve the mixed column step, and the last round of decryption, when I say the last round of decryption, this is actually this round, the round 10 here for decryption does not involve the inverse mixed columns step. Okay. So now let's go through each of the sub step. So the substitute byte step is very simple, or the inverse substitute byte step, which is done in decryption. So essentially, as I said, we'll have the state array, which is like a 4x4 array. Each element in that array is a byte. So we will substitute each byte in the state array with another byte. So that's what we are going to do. So how we are going to substitute each byte in the state array for a particular round to another byte, we are going to use a lookup table. So the lookup table is essentially, I have given this in kind of decimal itself. So you could convert this into hexadecimal if needed. Yeah, so that's part of your kind of working of the math to convert from decimal to hexadecimal. So let's do an example. So for example, let's say the actually I do have some question bank thing here. So let's say this is a input array or state array, and I want to let's say substitute this 4-1. So this could be like a question: given the following state in hexadecimal for an AES encryption round, perform the sub byte step, the substitute byte step, followed by the shift row step. So if I want to replace or substitute this byte 4-1, all I need to do is look up look up the table. Now all these values are in hexadecimal, so we have to make sure we kind of convert them into proper decimal values. So 4-1 hexadecimal. Again, hexadecimal, the kind of characteristic of that is each hexadecimal digit could be written as a 4-digit binary word. So 4 in binary is going to be 0, 1, 0, 0. So that is 4, followed by 0, 0, 1, that is 1. So if you try to, so in decimal also this is 4-1, right? So 4-1 in hex is also 4-1 in decimal. Which what I mean is this. So we will take this 4-bit quantity. This 4-bit quantity is 4 in decimal, and this 4-bit quantity is also 4 in decimal. That's what I meant. So this 4-bit quantity is still 4 in decimal, and this 4-bit quantity is 4 in decimal. On the other hand, if the byte we're looking at is 5A in hexadecimal, 5 is going to be 0, 1, 0, 1, whereas A is going to be 1, 0, 1, 0, 10. So that's going to be 5 in decimal and 10 in hexadecimal. Okay, so if I say something else, so if your the byte you're looking at is something like FD in hexadecimal, F is going to be 1, 1, 1, D is going to be 1, 0, 1, sorry, 1, 1, 1, 1, 0, 1, that is D. D is 13, right? So this is going to be F is 15 in decimal, and basically you're converting each of this into decimal. So each hexadecimal digit you're converting them into decimal. Okay, so if I want to replace, say, 4 1, the byte 4 1, all I have to look for 4 in decimal and 1 in decimal. So in that case, all I have to do is look the row 4 and the column 1. So row 4 and column 1, we have 131. Okay, so this 131 is in decimal, so we would have to convert this 131 in decimal to hexadecimal. So how do we convert the 131 in decimal to hexadecimal? Divide 131 by 16, right? So 131 divided by 16 is going to be if I divide 131 by 16, this is 128 is 8 times, so it's going to be 128, it's 8 times, right? So I can say this is, the quotient is 8, the quotient is 8, and the remainder is going to be 3. So the quotient is 8 and the remainder is 3. So I can basically say 131 in hexadecimal is 83 in 131 in decimal. We have 131 in decimal here, right? And 131 in decimal is going to be 83 in hexadecimal. Okay, and you can cross check. So we can, this is like if I convert 83, which is in hexadecimal, to decimal, all I have to do is multiply the 3 by 1, which is 16 raised to 0 essentially, and 8 by 16 raised to 1, which is 3 times 16 raised to 0 is 1, plus 128, which is 131. Alright, let's do one more thing. So if I want to substitute this byte 5a, I look for 5 in the row and 10 in the column. So 5 in the row and 10 in the column is going to be 190. So we are going to convert 190 in decimal to hexadecimal. So again I divide by 16. So if I divide by 16, it can go, so 190 divided by 16 is going to be like 11 times. So the quotient is 11. That makes it 176. So the remainder is 14. So this is essentially 11 is going to be B. So 190 in decimal is going to be 11. We have to write 11 in hex, and 14 the remainder also in hex. So 11 is going to be B and 14 is E. So I'll replace this byte 5a, right? So if you have 5a, we can replace, because what we worked it out is for 5a. So 5a will be replaced by be. Similarly, in the previous case, if you're replacing this byte 41, we'll replace this byte 41. 41 will be replaced by 83. Sorry, not 83, 83. 131 in decimal, but 83 in hexadecimal. So let's do one more step. If it is FD, we're going to look for 15 in decimal and 13 in decimal. So 15 in the row and 13 in the column. It is 84 in decimal. 84 in decimal. So looking to replace or substitute FD. And we found out the substitute value is going to be 84 in decimal, and 84 in decimal, if you convert that to hexadecimal, if you divide 84 by 16, the quotient is 5 and the remainder is 4. So that is 54 in hexadecimal. So and 5 and 4 can be written as it is in hexadecimal. So you are going to replace FD is going to be substituted with 5 4. Okay, so that's how you substitute each byte in the state array with another byte by using this lookup table. And for decryption, we use a similar substitute byte step. The only difference is we'll use a different table, an inverse sub bytes lookup table, but it is very similar. So you take up a byte in the state array and you will replace that with another byte by going to the method which I just described. Okay. Now the shift row step is very easy. So in the encryption stage, what we do after the substitute byte step, after each byte in the state array is substituted with another byte, we'll go to the shift row step. So the shift row step is basically kind of scrambling. So it kind of diffuses the bits throughout the array. So as we'll see here, the way it is done is the first row is not shifted, but the second row is shifted one byte to the left. So this is a shift row step done during encryption. So which means the S11, this byte is moved one byte to the left, S12 is moved one byte to the left, S13 is moved one byte to the left, and S10, when you move to the left, it wraps around and comes here. The third row is shifted 2 bytes to the left, so which means S22 moves here, S23 moves here, S21 wraps around 2 bytes to the left and comes here, S20 wraps around 2 bytes to the left and comes here. Now the fourth row is shifted 3 bytes to the left, so which means S33 comes here. And if you wrap around S30, it will come here because it will wrap around 1, 2, 3 byte to the left. S32, if you wrap around, it will be like 1, 2, third byte to the left, so this will be S32. And S31, if you wrap on 3 bytes to the left, it is 1 byte, 2 byte, 3 byte, so S31 comes here. So that's how you do the shift row step during encryption. The inverse shift row step done during decryption is quite similar. The only difference is here the shifting is towards the right instead of towards the left. So again, the first row is not shifted, and the second row, every byte is shifted to the right by one step. So S10 goes here, S13 comes here, S11 moves one byte to the left, S12 moves one byte to the right, and S12 moves one byte to the right. The third row is shifted 2 bytes to the right, so S20 is shifted 2 bytes to the right, S21 is shifted 2 bytes to the right, S22 is shifted 2 bytes to the right. So it comes here and wraps around and comes here, so this is S22. S23, if you shift to the right, it wraps around by 2 bytes, so this is the first position and this is the second position, so S23 comes here. The fourth row is shifted 3 bytes to the right, so here so we'll have S30 shifted 3 bytes to the right, so 1, 2, 3 bytes. S31 shifted 3 bytes to the right, so 1, 2, 3 bytes. S32 3 bytes, 1, 2, 3 comes here. S33 3 bytes to the right, it wraps around and comes here. So that's the inverse shift row step. So we will stop here and we'll continue with the mixed column step in the next video.